Hello, my name is Nigel Edwards and I lead the architecture team in the HPE Security Engineering organization. And our mission is to develop security technologies which are deployed across the HPE product portfolio. Today, I'm going to talk to you about Project Aurora Zero Trust Security Services. So first of all, what does zero trust mean to us? It's a buzzword that's used a lot today. So to us, zero trust security means that you don't trust anything. Instead, you measure and verify it before you allow it to interact with any other systems. And not only do you do it before you allow any interaction to occur, but you then continually do it to make sure it's in a good and trustworthy state. And that's the goal of Project Aurora. We want to be able to measure, securely measure or test systems so that they are verified by a trusted verifier wherever those systems are, be it the edge, in a shared colo, or in the cloud. And we are particularly focused on low-level attacks. If you look at this slide, it has lots of attacks which have occurred all over the stack, and we're particularly concerned about attacks that may occur to the system hardware. So we care about supply chain, to the kernel or hypervisor, or the firmware that's in the system. And the reason for this is those attacks are actually below the level of the system where most people interact with the system. If you're root or system administrator, if you've got compromised firmware, compromised kernel, compromised hardware, it's very, very difficult to detect using normal system administration tools. So the goal of Project Aurora is to measure the system. So I say again, we measure the system and verify its integrity. We don't use malware signatures or similar technology. And we want to measure the system continually and provide full attestation of its provenance and current state of the hardware, the firmware and operating system, the file system and container workloads, all the way up to workload and service identity management, so that a workload doesn't get any credentials, can't interact with other services unless the workload itself is authentic, and also the platform on which it's running, right down to the hardware, is in a known, good, trustworthy state. Now, to build a system like that, there are some important security principles. And the key takeaway from this slide is that a hardware root of trust and secure measurement are fundamental for security. Well, why a hardware root of trust? Well, a hardware root of trust cannot be subverted by an attacker. And in HPE's platforms and our ProLiant servers, ILO Silicon Root of Trust, ILO is our BMC, or baseboard management controller. And this is the management chip that's on all our ProLiant servers. It's our own ASIC. And the first thing that happens when you apply power to one of these servers is that ILO becomes active. And the first thing that happens within ILO is there's a state machine burnt into the ASIC. That state machine is immutable, so an attacker cannot change it. And the job of that state machine is to verify the first block of code that's going to be loaded into ILO. And then ILO, just inside the BMC, goes through a secure and measured boot. And then what happens is that ILO will verify all the firmware in the firmware within the platform before it loads that firmware into the other chipsets in the platform. So we know we've initialized the platform in a known good state. And then, of course, the job is to extend that so the platform stays in a known good state. Now, another important point is that authentication or code signing, although great and very useful, is on its own is not sufficient. Now, I think nobody's going to argue that rigorous and secure key management is not important, but mistakes happen. So keys get stolen, people get tricked into signing malicious code. So we're seeing a lot of malware today that is now signed. So that means it's important to measure everything as well as verify signatures, and then measure that and compare that with reference measurements to ensure that you've actually got what you want and expect to be running on the system. So the final principle is the one of secure measurement. Secure measurement means that every component, before it is able to affect system state, is measured. And furthermore, it is measured in such a way that even if it's malicious, it cannot take its own measurement back. It can't remove its own measurement without that being detected. And for that, we use trusted platform modules, or TPMs. So these are industry standard secure microcontrollers. They're standard now on our ProLiant servers. And amongst other things, they're designed to support secure, tamper-proof platform measurement. So we use it as the root of trust of measurement within Project Aurora. So the goal of Project Aurora is to build a chain of trust from the hardware all the way up to the workload. And it doesn't actually just happen when the platform's powered on. We also worry and do a lot of work in the supply chain to ensure we have a secure supply chain. And recently, we introduced Trusted Computing Group standard platform certificates in our servers. So these are signed X509 attribute certificates, which are an inventory of the hardware, the principal hardware components that are within the server chassis when it leaves the factory. So that enables you, when you receive the server, to ensure that it's not been tampered with on the way from the factory to you. And then when you power it up with Project Aurora, we can ensure that we build this secure chain of trust all the way up to the workload. So this slide is a schematic of a server instrumented with the Project Aurora security services. And so what you can see here on the orange boundary are chip isolation boundaries, because I want to draw to your attention the platform BMC, in this case ILO, and also the trusted platform module. So these are separate chips. So there's an isolation boundary between any malicious actor that's running, that has gained access to the operating system, which is what we're concerned with measuring and monitoring here with Project Aurora. So if we look at the BMC, ILO BMC first, so we have the capability, as I explained, to measure and verify the firmware. We also have an OS intrusion detector, which is monitoring the running kernel continually for signs of tampering, which may be an indication of malicious activity. When the platform boots, we boot initially HPE UEFI. So we go through secure and measured boot, which is a standard capability in UEFI, but we also measure the hardware that's in the platform. And that measurement is protected with the Trusted Platform module, Platform Configuration Register, or PCR number 6, if you're familiar with TPMs. So that even if you happen, unfortunately, to boot a malicious operating system, that operating system can't tamper with the hardware that was measured by UEFI. In the operating system kernel, we've got a couple of kernel modules. There's the HP TOS kernel module, which is responsible for measuring, helping with measurement of the integrity of the kernel, and I'll explain how that works in a few minutes. The USM, or user space monitor kernel module, is responsible for monitoring critical system processes, endpoint protection systems, for example, and that gets reported back to ILO. We're using IMA, the Linux Integrity and Measurement Architecture, which has been in the Linux kernel since I think around 2009. So we use that, and I'll show you how we're using that in the video of a demo that I will show shortly. And then in user space, we have a platform agent. The job of the platform agent is to perform attestations, which are secure, basically a way of securely measuring the platform state. If you're familiar with trusted platform module technology, you'll know, you might be aware of the concept of a quote. So we go through a quote with the remote Aurora integrity engine, and as part of that, we ship the TPM and authenticate the TPM platform configuration registers, as well as system logs, which will be authenticated by the platform configuration registers to the Aurora integrity engine, so we can verify the state of the platform. The final piece here is the Spire node agent and plugins. So Spire is a open source service identity management system. So services and workloads can be issued X509 credentials or JOTs. And we have plugins for Spire, which ensure that for a service or workload to get a credential, not only does the workload have to be authentic, but also the entire platform, right down to the hardware on which that workload is running, has to be in a known good state and verified by Project Aurora. So if you take away one thing about what is maybe unique about Project Aurora, is we're monitoring the operation and integrity of the system from the BMC, and we build a chain of trust from what happens when you first power on at the system, with the BMC becoming active, through to what's going on in the operating system. And that chain of trust is still there at runtime, with the BMC monitoring the kernel and extending that chain of trust all the way up to processes that are running in user space. This slide just shows the deployment scenarios we have for Project Aurora. So the key takeaway here is that servers that are being monitored can be in an edge or colo, and the Project Aurora integrity engine, which you see here on the right hand side, could be on-prem, it could be in the cloud, it can be remote, or it could be located close to in the same data center as a server. We have well-defined APIs for integrations into security information and event management systems, or SEMS, or other services and monitoring services. We also have a dashboard, and you'll see the dashboard shortly in the videos of the demos. Okay, so now I'm going to take you through some videos of a couple of demos that we have of Project Aurora. So the first demo shows how we monitor the hardware within the physical server. And on the slide here, you see some documented cases of hardware tampering that have been known to occur. These are practiced by nation-state actors as well as criminals. So you may remember that when a server instrumented with Project Aurora boots, HPE UEFI will measure the hardware and protect that measurement with the TPM, and then later the Project Aurora platform agent, when it attests the state of the system, will the TPM will authenticate the hardware measurement, and the actual log of the measurement will be shipped back to the Project Aurora integrity engine. So in this video, then you can see here the Project Aurora user interface, and we just got a single server that we're monitoring. And because it's easier with a running server, just to change the database of expected hardware components, and so that's what we've done there. Just run a little script on the server to change on the Aurora Integrity Engine server to change the expected hardware configuration. And you can see here now the project Aurora Integrity Engine has alerted us to changes in the hardware that's in that server. It's no longer in the expected configuration, and you can see a DIM has been changed, and we're also seeing an unexpected PCI device. In this case, the network controller is not what we expected. It could be a disk controller, and that could be seriously bad news. So if that's a malicious device, it could be monitoring network traffic. If it's a storage controller, it could be landing malicious files onto your disk, no matter how many times you reinstall the operating system, for example. Of course, this could be a legitimate service engineer's activity. So we also have the ability, as you can see here on the right-hand side, if you look carefully, to update that server and tell the integrity engine that this is fine. Service engineer has been in and made some changes to the server, and this is all expected. Or it may not be what you expect, and you want to go and investigate that server. Okay, so the next demonstration that I wanted to show you was of how we monitor the kernel integrity, in particular how we can detect rootkits and other kinds of kernel tampering. So a rootkit, in simple terms, is a kernel rootkit is a malicious kernel module or driver, and its job is to hide attacker files, processes, network connections. And if you have one of these, it's very hard to detect if you are even a root user, because the rootkit is going to be filtering out any sign of attacker activity. And using this, there have been documented cases of persistence being obtained on a system for months and even years. You can see some examples of rootkits that are known on the slide here. Droverub is attributed to the Russian GRU, and this was published by the NSA and FBI in August of 2020. And last year there was an eBPF rootkit unveiled at Black Hat. And we can detect all of these rootkits. I'm going to show you shortly us detecting the Droverub rootkit. Now, the way we detect these is that ILO is continually scanning kernel read-only data, kernel modules, kernel executables. And the way we know what region we're scanning physical memory, and the way we know what regions of physical memory to scan is that this HPTOS kernel module, as soon as we've completed secure measured boot, reports back the physical addresses of the kernel to our ILO BMC, so that the OS intrusion detector can then begin monitoring. And we scan the relevant parts of system memory once every 10 seconds, so we can detect a rootkit in 10 seconds or less. This slide shows at a very high level a very simple rootkit. It's like if you like, a first generation rootkit. And the basic idea is that they hook the system call table to divert any system calls through a malicious kernel module, which scrubs any attacker files, network connections, processes, and so on. Droverub actually hooked much deeper than that. But the principle is still the same: scrub activity of the attacker. But ILO is a separate chip. It's not affected by any changes to the kernel. It's still monitoring and can still report the changes to the Project Aurora integrity engine. So the next demo then is of Droverub. There are no publicly known samples of Droverub that I'm aware of, but there's an excellent report from the NSA and FBI, and from that we reverse engineered our own benign version of Droverub using the same hooking techniques that we use, which we hadn't seen before, but we're not relying on signatures, we're just measuring integrity. So as you'll see, we can still detect its presence. So here we're loading Droverub, or our benign version of DroverHub, and if you look carefully, you can see the modules invisible, the processors invisible, network connections are invisible. So at that point, the attacker is hidden to a normal root user or even a normal user. And you can see we've alerted here. And if what we're going to do is click in onto that, and you can see that there are two problems that we've discovered with the kernel. The first is the fact that we've got a new kernel module at all, which we've called DroverHub just for the purpose of the demo. And the second is actually that there has been a corruption of the kernel executable. And that corruption is actually DroverHub embedding itself and making changes to the kernel executable so that it can hide attacker activity. The second demo that I wanted to show you was the demo, which is not a rootkit, but it's a privileged escalation, which came out last year using bugs that were in the iSCSI kernel modules. And so just quickly run the video. So this is the proof of concept GitHub repository. And you're looking here now at the ILO amplifier dashboard, and what we're doing now is downloading the demo, and the POC, we're making it, building it, and now we're going to get ready to run it. So you can see there's nothing of interest in the tump directory now. We run the exploit, and what you'll see is that now there's a root proof file in /temp. So we got root access. Meanwhile, what we've discovered with the monitor in ILO is that the kernel modules, the iSCSI kernel modules have been loaded, and then they're unexpected. And not only that, the kernel executable code was changed. So you can see, in fact, what's actually happened there is it's exploiting buffer overflows in the iSCSI kernel modules, and then using that, it's actually hooking and modifying the kernel executable code as part of the attack to get root user access. And that's what we've detected. So you can see, basically, Project Aurora is continually monitoring kernel integrity and is able to detect rootkits and other kinds of attacks on the kernel. The last demo that I wanted to show you was our use of IMA, or integrity measurement architecture, to detect unwanted malicious files on the file system. So this is higher level malware, but it could be a backdoor, it could be ransomware, it could be cryptojacking or crypto mining software, or it could be a change to a malicious change to your container runtime, for example. And there are many documented cases of this kind of thing. The few are shown on the slide. So here we're showing now a quick video of how Project Aurora works with IMA. So what you see here is a server that we're monitoring, and what we're going to do is just run a script which will dump some unwanted files and make some unwanted file changes on that server. And then we're going to trigger an attestation so that the server will upload its state to and attest the state to the Project Aurora integrity engine. And now you can see there are a couple of alerts associated with that server. And if we click into those, what you can see here is that there are several problems with the server. So first of all, we've detected changes to the container runtime, and because we've got known reference measurements for the container runtime, we've determined that that is critical. The container runtime should not have changed. The binaries, the executables in etc fonts are unknown, and so we just flagged those as warnings. So this comes from a real world example, which we are familiar with, where crypto mining software was actually installed in etc fonts on a Cray supercomputer at the University of Edinburgh. But we don't know. We just don't know what that executable is, so we flagged that as a warning. But that is configurable. If you didn't want any unknown executables, you could make that a critical warning as well. Okay, so just wrapping up then, what we're doing in Project Aurora is building a secure chain of trust using ILO from the time that the platform is powered on. We verify the hardware components in the platform. We verify the firmware and operating system. We extend the chain of trust up into the operating system kernel and file system, all the way up to the workload, service and identity management. So unfortunately, in the time available, I didn't have time to show you the integration we have with Spire, but essentially the Spire agent will only issue credentials if the workload is authentic, and consulting the Project Aurora integrity engine that the platform on which the workload is running is in a known, trusted, good state. So with that, we reach the end of the presentation. I want to thank you for your attention if you're still listening to this. And if you wish to know more about Project Aurora, please check out the URL at the bottom of the slide. Thank you very much indeed for your attention.